Last week of actual new content for the course, and next week we only have one lecture, and that's a revision lecture. So what I'd like you to do is to think about what you want to ask at Monday's lecture in a week's time, because that lecture will be driven entirely by you. I'm going to bring to that lecture sample exam questions and so forth, and I can step through the exam a bit, show you how the exam structure works and that sort of thing. But really, it's up to you to drive the lecture. And if you have questions you want to ask, put them on Piazza ahead of time, and we'll try and I'll put a post on Piazza to invite you to make those questions. Or maybe I'll try and do that at the end of this lecture. And you can put your favorite questions there. The best questions to ask are, you can ask procedural ones like, how do I do this, or how's the exam going to work? You're welcome to ask those. Hopefully that's all clear to you, but if something's not clear, go ahead and ask that. The other ones are things like, how do I approach question 3 in the practice exam, or how do I approach question 6, so I don't understand what the question is really asking. That sort of stuff's great, okay? And I will try and answer all those questions that I get at next Monday's lecture. Now let me jump to here. And I want to remind you about the exam. The exam details are, it's written in here as being on the 10th of November. But remember, you've always got to go to the university timetable. Whatever I tell you is not the official thing. It's a university timetable that is official. Okay, so you need to go to the university timetable to know for 100% sure when the exam is. Still, last time we looked, it was 12:20 p.m. on Wednesday. Now, I've had a handful of people approach me. Nearly everyone who approached me was either in the Middle East or in India. If you're living in one of those parts of the world that is basically to the east of New Brunswick in Canada, or to the west of Kolkata in India, anywhere in that region there, then feel free to go to Piazza, look at my post about the exam and time zones, and send me a private message about your situation, and I'll update that. Oh, I notice here this is not quite up to date. I updated it last week in the lecture and on the Piazza post, but you can see here it says Karachi. Actually, I changed it to Calcutta in India. So, well, India time anyway, New Delhi, whatever. All right, any questions on anything relating to the exam? Please put them in the chat, and Leo will ask them. Now, excuse me while I just have another sip of coffee. Now, the no labs this week. The one-to-one consultations are going on. Remember, there are 9 every week. And if you're trying to prepare for the exam, nothing better than getting one-to-one consultation. If you go to a one-to-one consultation with a particular question, like, I don't understand how to do question 2 in the sample exam, and you've got your working there, you say, look, I've tried this and it's not working. That's a great, very concrete thing to do, to take to a one-to-one consultation. So there's 9 this week, 9 next week. It's 18 one-hour sessions for you to go to ask questions. So please make the most of those. As I'm sure you're all acutely aware, the main deliverable for assignment 2 is this Friday. And remember, there are no extensions in this course, no extensions. We just look at whatever went into Git and was pushed to Git, and whatever we saw at 11:45, right before the lecture on Friday. And if you have some terrible thing happen to you, don't stress. The university has very good special consideration processes. All the details are on the course webpage about what you need to do if you're not going to be able to make the deadline. There are no extensions, but we can give you special consideration if that's appropriate. Make sure you test your game.jar standalone. If you're lucky enough to have different group members with different operating systems, say Windows and Mac OS, that's excellent, because you can make sure that your game.jar works in the different operating systems. Make sure you can make it work from the command line if you can. That's a good thing to test, because what we really want is for your tutor to be able to grab that jar file and test your whole assignment from that jar file, independent of IntelliJ. Make sure you're thoughtful about your originality and contribution statements. Now, don't forget your presentations. You're welcome to include a demo in there, I think. We really want to know how the approach you took to the design and anything interesting you did. Which reminds me, some people have asked a number of times about the last stage of the COMP1110 assignment. where you're supposed to do interesting variations. Interesting variations does not include anything that I actually asked you already to do. If I already asked you to do something, that's not an interesting variation. It's got to be things that I didn't already ask you to do. Okay, so that's for that I think the last task in the Comp 1140 assignment. Anything there in the chat, Leo, relating to the assignments or the labs or anything, admin? Nope. All right. If you haven't been paying attention, we're right on the home stretch of the whole course, and we're kicking off now with 3 core computer science units, the first of which is about files. To some extent, I'm teaching a little bit about the way Java does files, but really the main thing I really want to teach you here is more deeper principles relating to files. So let's get started with this now. So a stream is a standard abstraction used for files. What the heck's a stream? So I'm sure most of you know what the English language meaning of the word stream is, right? It's a water going down a hill. That's a stream, okay? Why do we use that as the abstraction? Well, hopefully you'll get a little bit of intuition for that as this lecture goes on. And the word stream in this setting means it's a sequence of values that are read or a sequence of values that are written. And why? Well, because the stream reflects the sequential nature of file I/O and the physical characteristics of the media in which files traditionally reside. Okay? So, sequential nature of file I/O. So a stream is sequential, right? So you see water or things coming down a stream, they come down one at a time. That's kind of what we think of when we think of a stream. Things are coming at you one at a time. Now, that's perhaps not how you think about a file naturally, but that's how we model it in an operating system, and that's how we've done it since the beginning of operating systems. And there's a reason for it. And it starts with this. So I'm interested to know how many people know what that thing is. I wonder if anyone does. I guess some of you know what that is. But when I was a kid, that was how we stored our music, believe it or not. I'm aging myself here significantly, but we stored music on these things really early on. What this is there's 2 wheels there, and there's a thin plastic tape wound onto those 2 wheels, and you can see it. There's not so much on the left. There's a little bit of black plastic tape there, a dark brown plastic tape there, and quite a lot over there. And what would happen is this thing here would wind around, and the tape would go from this reel inside this plastic thing here, across here, and then up and then onto this one. And then there'd be an electronic device here which would read signals from the tape, because this was plastic tape charged with some sort of magnetic material, and you could record stuff on there. And as the thing went past, the electronics would read the signal through the magnetism, and then there'd be an amplifier, and then you'd hear the music. Okay, so that's how we listen to music those days. So you need to pause. If you haven't actually used one of these, you should pause just for a moment and think about what that means. What it means is that you can't, what happens if I want to jump to a random track or shuffle, right? How do I do that? Can't do it, right? Because if you want to jump to a different part on the thing, you've got to make this wheel spin around to get to the place in the track where the thing you want is, right? So it's a real pain, because not only that, but you have to know how far to go, right? And so one of the things you do when you had this, you'd have a piece of cover paper or cardboard, and you'd write all the tracks on there, and you have the number that is the count of how many spins of this wheel that particular track was at. And so if you wanted to get to a particular track, you hit a button and you waited till a little counter went to that number, and you go, oh, okay, this is about where that track starts, and you press play, and if you're lucky, it would come on to the track you wanted. Okay, and then what happened, the other thing that was funny about these things is that when you got to the end, you could actually turn the thing around and keep playing from the other side. Okay, so why am I going into all this? You think, why, he's just talking about music history. No. This is actually directly related to the way they stored data on computers back in the day. And now hopefully you can see here that tape whizzing past the read head, this is a read or write head down here, that would be reading the tape. That is the idea of a stream. So the tape keeps streaming past the read head, and it's reading, or if it's recording, it'll be writing by magnetizing the tape. Okay, and that's the notion of a stream. And you can see it's really annoying to get to a different part of the file, if that's your file rather than just music. To get to a different part of the file, you have to do weird things, and it's hard to get it exactly right. because you're going to have to somehow or other spin that wheel around to exactly the point where you want it, and so forth. And getting that exactly right is actually really difficult. Okay, now what are these? Well, these are actually, that's like an ancient photograph. This is before my time, believe it or not. That's a long time ago. But what you see in here is actually a really fancy high-end version of this. This stuff here is what kids listen to music on. This thing here is a high-end computer, and that's its storage system. And you can see these things here, they're almost exactly the same as this, just on a giant scale and very high quality. And these people here are operating the computer. You can see from their headsets, apparently. I don't know what they're doing, but that's some sort of old computer storage system. Okay? Now, this here, on the other hand, is actually relatively recent compared to that thing. And these things still exist. Okay? So these are very similar to that there. Okay? And instead of storing analog signals, these ones here are storing digital signals. And this thing here, when I was a PhD student, we used these all the time. And they still use these until... in ANU Computer Science, they probably still use these until about 10 years ago. What was so good about this? Well, the storage density. You could store an incredible amount of data on these things. They actually had very high storage density. So one of these things could store very many gigabytes of data, if I recall correctly, which is a lot more than you could store in other ways back in at that time. So it was actually one of the most effective, cost-effective, because they're very cheap, really. It's a bit of plastic and a bit of plastic tape. Very cheap. And can store a lot of stuff. So we use these all the time. This is where a lot of data was stored, and particularly for backup. So these things, this device you see here, made by Sun Microsystems, was sort of a ubiquitous backup device. And not only that, but people who are storing a huge amount of data, like astronomers who have incredibly large amounts of data, they have things called tape silos. So it's a big thing with thousands of these tapes and a robotic arm that could go and pull the tape out, put it in a playhead, against a playhead, and find the thing you were looking for. Okay, so and until relatively recently, large companies like Google and Facebook and Twitter and so forth used these things for archival storage because they're so effective. Anyway, the point of this giant digression here is to explain to you that storage on tapes was a thing and still is a thing, and that is where the concept of a stream comes from. You need to understand the concept of a stream because that's fundamental to file I/O. Now, does anyone know what this is? I'm sure a lot of you know what that is. That's a turntable, right? And that's another way of listening to music, okay? And this thing here spins around. But what's really cool about this compared to the tape is you can lift this up and move it to a different place. Okay, so if you want to get from the song here on the record to a song here, you don't need to spin this thing around until it eventually gets there. You can lift this guy up and then drag it across and then drop it down again at the place you want. There's a bit of guesswork in getting it in the right place, but if you look very carefully at the pattern of grooves on the thing, you can actually easily see where you want to go. That, again, you think, why is he digressing into music? I do like music, but that's not the reason why I'm digressing. The reason why I'm digressing is that's actually really closely analogous to how a hard disk works. And hard disks are still really widely used. I don't think there are any in this room here. I've got computers around me. I don't think any of them have hard disks in them, but still, the hard disks are used in many situations. And this is what a hard disk looks like on the inside. And this thing here is actually remarkably similar to this. And this thing here is the ARM, which is remarkably similar to this. And what you have again is this concept of a stream of data. So as this groove goes past the stylus on this arm here, as the groove goes past, that is very much like a stream of analog signals that goes past. So again, this concept of a stream. All right, so hopefully you've gotten the motivation for why we keep talking about streams when we're doing file I/O. Now the classes input stream and output stream are, by the way, Java has new I/O, NIO. I'm not going to discuss it here. Why? Because this lecture is not so much about giving you fancy ways to do file I/O in Java. You can do that in later years or in your spare time. This is more about telling you, notice this is not a J lecture, it's a C lecture. I'm trying to talk to you about the primitive basics of how files work. And we're just using Java because that's the language this course is done in. Okay, so I'm not doing NIO, which is the new file I/O in Java, which is quite convenient. Instead, I'm giving you more a first principles look at it. Okay, so how do you work with this? First of all, you have to open a stream, and then you read or write from the stream, and you do it in bytes. Now, this is interesting. So it reads bytes from the stream, and then you have to wrap operations in a try clause. Why would you have to wrap operations, file I/O operations in a try try-catch clause? Anyone know? The answer should be clear to you if you went to the exceptions lecture. Okay, you have to use try and catch for anything that is by design likely to have an error. And I/O could easily have an error. Why? Simple. You could have typed the name of the file wrong. Very easy to happen, particularly if you took it from input and the person typed it in wrong. So it's quite possible, it's quite much by design that there could be an error in opening a file. So we have a file opening error, file not found error is completely normal. So it's an error, yes, but it's a completely normal error. It's an error that you can anticipate. And the other thing is that someone could yank the USB cable or whatever it is on your thing, and so the whole disk may not be there, or they could do it right in the middle of reading. So there are lots of possibilities where file I/O can fail, and so try-catch clauses are important. And you'll find this out anyway. You don't need to remember that, because if you use IntelliJ and you start typing stuff about file I/O, it'll say, hey, you need to wrap this in a try-catch block. And we usually use the finally clause to close the streams, because there's a concept of opening a stream and closing it. And what's interesting is the operating system, so Mac OS or Windows or Linux, whatever it is, underneath will have a bounded number of files that can be opened. They're called file handles at the OS level. There's a limited number of them. They're not an infinite resource. And so it's good practice to open, after you've opened one, to close it when you're done with it. Okay? So we use the finally clause to make sure that that things are closed after we're done. Now, if we write really trivial programs like we're going to do in the lecture here, that hardly matters. But if you write some very complicated software, it's possible you'd end up in a situation where you just kept opening files and not closing them. If you did that, your program would eventually crash, because you'd use up all the available file handles in the operating system, not because of Java, but because of the operating system. And the last point is a really weird one. Ints are used even though bytes are transferred. Okay, so when we have a byte stream, which is what we're talking about in this slide, okay, we're moving byte from the disk into some buffer or something in the into the program. Okay, but what we get back from the operations are not bytes but ints. Why is that? Well, we want a byte to be read, but we actually need two bits of information. One is the whole byte that got read, which is 256 different values, right? 2 to the power 8, 256 values. It's one byte. But we also need one more piece of information. What's that? Did it work or not? Okay, so we need to be able to signal whether this was successful or unsuccessful, in addition to getting the 256 different values, which means we need like 257 different values, which doesn't fit in a byte by definition, right? So we need something else. So what we actually have is we use ints. When we say we, Java uses ints. Okay, so when I read something, even though I'm only reading a byte, I get back an int, and then it uses the -1 to indicate I got to the end of the file. Okay, so it couldn't do that if it just returned a byte. We'd only get the byte back. We wouldn't know if the byte was valid or not. If we got back 0, we'd go like, did I just read a 0, or does that mean that I'm at the end of the file? Who knows? So that's why it returns an int instead of a byte, which is a source of confusion for very many people, that when you're reading a byte, you get back an int. Okay, character streams. In addition to reading byte streams, which is that slide, you can also read character streams. Okay, so when you're reading or writing characters, same deal. Ints are used even though chars are transferred. Okay, so char is 16 bits, but you get an int back. I/O buffering. Right, now let me talk to you about buffering. To talk to you about buffering, I need to talk to you about cricket, or your favorite summer sport, whatever that might be. And if you're someone who lives in Melbourne maybe, or Sydney even, and has come to Canberra and watched the cricket at Manuka Oval, you know that the service there is terrible because they don't know how to deal with crowds, right? It's not like the MCG or some other big ground like that. And the place you notice it is when you go to get a drink. Right, so I'm going to explain. So one of the times when I was there, I was so frustrated. It made me think about my computer science lecture, and so I want you to think about this. It may help you understand the concept of buffers. Okay, so if I go to the store to buy a drink, right, and I go to the store. Now, what's important? It's summer, so the drinks need to be in a refrigerator, right? Okay, so you need a refrigerator for the drinks, but there's 10,000, 15,000 people, so you need a very big refrigerator. But the person selling the drinks is not inside the refrigerator, obviously, so they're somewhere else. But all the drinks are in the refrigerator, so you've got a little bit of a problem here. How do you deal with this problem? Okay, so the one way to do it, now forgive me, this is a little bit naive, but think about this. I go to the person and I say to them, hey, I'd like a Sprite, please. And the person says, sure, just wait a second. And they walk to the refrigerator where there's 10,000 drinks, they find a Sprite and they bring it back to me. Okay, that's not very efficient, really, is it? To make things worse, what happens if I go there and I say, hey, I'd like 2 Sprites and 2 Cokes, please? They're like, sure, no worries. And they go off and they come back with 1 Sprite. And I'm like, no, I asked for 2 Sprites and 2 Cokes. Then they're like, yes, I know you did. And they walk off and they come back and they've got another Sprite. I'm like, really? 2 Sprites and 2 Cokes. And they go back and they get a Coke. And they go back and they get a Coke. And so they're getting each drink one at a time. And you know, this would drive you crazy if they did this. So it should be pretty obvious to you, we want a slightly more efficient solution to the drink situation than that. Okay, so what do we do? So you can put suggestions in the chat if you want to solve this drinks problem, but the analogy goes to files, okay? So there's a reason why I'm going down this pathway. So think about what we should do. I mean, has anyone got any suggestions? What's the solution to this problem? There is a real solution to this problem, and the word that we would use, there's a couple of words we might use in English to describe the solution to this problem, and they're actually words that we use in computer science as well. And these are real things that we do all the time. And I'm going to demonstrate, and you think, you're probably thinking, that example Steve gave is the most ridiculous example because the amount of time it takes to go get the drink from the refrigerator, walk there and come back is so long, that's clearly not going to work. But I don't know if you realize it, but this is actually a mild example compared to what happens in a computer. That's actually a mild example. Now the words, any suggestions there, Leo, online?
Yeah, a lot actually. You were suggesting we should get all drinks at once and put up a fridge at the counter, have a small number at the counter, and mix all the drinks into one. So
okay, lots of great suggestions there. Okay, lots of great suggestions there. Now we can't have all the drinks at the counter. That's not an option because there's 10,000 drinks and the counter's only so big, right? So we can't do that. And that's what's motivating the problem, is we need the 10,000 drinks in the counter, but we just need a few here. So ideally what we're going to do is we're going to grab a bunch of drinks at once and put them here, and every now and again go get another big pile of drinks and put them here and have something to keep them cool temporarily here, maybe just some ice or something, or a small fridge, or just a bit of ice or whatever. Maybe they don't even need anything because they're coming in so cold and they're only here for a few minutes, so that will all work. And just every time I go to the fridge, I don't bring back 1 drink, I bring back a couple of cartons of drinks every time I go to get more drinks, right? That'd be much more sensible rather than getting 1 drink at a time. Okay, and that's exactly what we're going to do in today's lecture. And that concept of having the drinks here is what we might call in English a cache. Okay, you got a cache of drinks here, a buffer. A buffer is the cache and buffer are the words we use in computer science. So you've got a pile of stuff here, and most of it sits out over there. And the reason why most of it sits out over there is it's a lot more efficient to have 10,000 drinks in one huge room than to have lots of little things with the drinks. Okay, and so we just have them here temporarily. All right. That's the motivation. And now let me keep going. So reading data 1 byte at a time is costly. That's like getting a drink from the refrigerator 1 drink at a time. Crazy idea. So we use buffering to absorb some of that overhead. Okay? So in Java, we've got a thing called the buffer reader and the buffer writer class, which can be used to buffer data that got read or written by the file reader or the file writer. And importantly, we have to make sure the buffer is flushed. Okay, so if someone at the end of the day wants to count all the drinks in the big fridge, make sure nothing got lost, we need to make sure all of the caches, all of the little fridges or little ice buckets, all the drinks got taken back and put in the fridge at the end of the day, so they're all in one place again. You got to flush stuff out, okay? Otherwise, you get the counting wrong, or you forget about the drinks that were left here. Okay, so we got to flush stuff out, okay? And close or close the file. Now these are the numbers I wanted to show you. Okay, well I can get you to guess, right? I get you to guess what's the difference between getting something from what we call a register, which is really close to the program, getting something from memory, or getting something from a disk. Well, the numbers are right here. So notice a register takes in the ballpark of a nanosecond. Getting it from memory takes in the ballpark of 10 or so nanoseconds. It depends a lot, but very much in the ballpark. Getting it from a solid state disk is something like 100 microseconds, and from a disk, a spinning disk, 10 milliseconds. Okay, so the difference between this 10 milliseconds and this 1 nanosecond, so that's 10 million times slower. 10 million, okay? So again, if the walk to the refrigerator was 10 meters and it was only 1 meter to get, or so not 10 meters, say it was 100 meters to the big refrigerator and 1 meter here, that's 100 to 1, which sounds like a crazy ratio. But here we've got 10 million to 1, 10 million to 1, okay? So I want you to understand that the difference here is absolutely enormous. It's not like walking 100 meters to the other fridge. It's like doing that, 100,000 times, right? That's crazy, right? So you're not going to do it. It's way too expensive. I say command line I/O. Historically in operating systems, we have 3 standard streams which are embedded in the foundations of the operating system, if you like. One's called standard input, which in Java is reflected as system.in. Another one's standard output, which is system.out. Another one is standard error. Now, in and out, you're familiar with all 3 of these, and very often, depending on your terminal, standard error gets colored a different color because that's the one that's used for errors, and also it's typically not buffered. Okay, the other 2 are typically buffered. Okay, so when you print something to standard out, it may not appear on your console until something happens, maybe a new line, or maybe a certain number of characters have been printed. It's not guaranteed to come out instantly, whereas the standard error has better guarantees. And this is important for a bunch of reasons, and that's why we use standard error. That's one of the reasons why we use standard error for debugging, or conversely, we use standard error for debugging, which is why we don't do buffering on standard error. And here's an example of the syntax. So if you want to read a byte, so you read a byte in, notice you've got to do this little cast here. That's because this thing, what does it return? It returns an int, right? That's returning an int, and then you're going to cast it to a byte B, and if you want to write it, you have to do that. You could flush it, or you could write it to standard error like that. You don't need to do a flush for standard error. All right, time for our mini quiz, and then we'll do some coding. Okay, so there's your mini quiz, and let's write some code here. And what we're going to do first is, hang on, new file, and we're going to write just a very basic one that does standard I/O. So file, what I'm going to call it standard I/O. Okay, like that. And what I'm going to do is read a byte from standard input. Standard input's the keyboard, right? So let's read a byte from the standard input, and to do that, let's just do this. We'll say now remember, when we do a read, it's going to give us an integer, okay? But we can do it like this. We just do this byte b equals we've got to cast it system. Oh, hang on, we're going to do a PSVM. Main method declaration. There it is. System dot main system dot in. We're reading from the keyboard. That's the input stream. Dot we're going to do a read. Okay, it's going to give us a byte. And oh, why we got the squiggly red line there? What's that about? Add exception. Okay, exception because all of I/O could generate an exception. I mentioned that before. Okay, so what we're not, because it's a main method, we're not going to add that to the method signature. We can't. But what we can do is surround with a try and catch, and we just do that really easy in IntelliJ because it tells you when you need to catch the exception, and we'll even write the code for you. Okay, so here this is an I/O exception. If something goes wrong, we'll get an I/O exception, and we'll get some message here. Okay. Now, what we're going to do is actually what we can do, just to be a bit more clear, we can say this. We say int I equals system.in.read, just to make this really verbose and really clear. Go like that, okay? And then we'd say cast the integer I into a byte. Now, if we're going to check if something strange happened, or like the end of file or whatever, we can write some code in here. And we're going to do that in a few minutes in the next example. But for now, we're not going to do any checking. We're just going to do that. And remember, the reason why we have an int here is because we need the 256 values for the byte, plus we need another value to tell us whether it was successful or not. Now what we're going to do here is we're just going to do a print that out, okay? So I just spent the whole weekend coding in a different editor, different IDE, and all the shortcuts are different. And I'm just forgetting. All right. There we are. Now, so let's just run this program. So I should be able to now type a key on the keyboard, right? And it should print out what I typed, right? Okay? So tell me if you think I've made any mistakes here. But let me try and run the program. Okay, so what I'm going to do is I'm going to type the keyboard key 5, and I want you to write on the chat what you think is going to get printed out. Okay, I want to hit 5 on the keyboard, and I want you to write in the chat what's going to happen. Okay, so we're going to run this, and if you can tell me what happens, Leo, what people said on the chat, that'd be great.
Hey Steve, they haven't got response. They haven't got any response yet. But Ethan asked a very interesting question. Why can't we easily cast integer to Boolean in Java? In C, the reason we return -1, 0, and 1 is that we can use it in if statements.
Wait a sec. I didn't quite follow the question. In C, there is not a Boolean type. Okay, you don't have a Boolean type in C, so you use integers for Booleans. So that's what you do in C. What's the question though?
Why can't we easily cast integer to Boolean in Java?
Because it's a different thing. So a byte is an integer. In Java, a byte is an integer that's 8 bits wide. Okay? A byte is an integer that's 8 bits wide. An int is an integer that's 32 bits wide. And a long is an integer that's 64 bits wide. And a char is an integer which is 16 bits wide. They're all integers. Okay? They're just different numbers of bits in precision. A Boolean is not an integer. Okay? So I don't think you can cast. It must have been I never tried. Let's try. These things are always worth a try. Yeah, no, you can't cast that because it's not an integer. A Boolean is not an integer. It's a true-false value. In C, they do this stuff because it's an old language, and they just basically fake it. Whereas here we're saying these things are actually integers of different widths. A byte is an integer of different width, and int is an integer of a different width. A Boolean is not an integer. It's a true-false value, which is not the same thing as an integer. So that's why you can't cast. There you go. Inconvertible types cannot cast from int to Boolean. Okay, that's a good thing. That's because it's a well-designed language. C is a very old language that allows you to do all kinds of dangerous things as a result because it's very weakly typed. Okay, it's called weakly typed language. And lots of other languages will be like Java. You can't just sort of smash and basically, what's going on in C is there's an assumption about the way you're representing Booleans. And you're saying, okay, I've got this integer here. Now I'm assuming Booleans are going to get represented this way. I'm going to smash this thing into a Boolean. Okay, we can't do that in Java and in a lot of other strongly typed languages. All right, I didn't get to answer the question. Okay, so let's see what happens. I'm going to type a 5 on the keyboard here. And what happens? Okay, what do people say? Did anyone have any suggestions on the chat there?
Yeah, a lot.
Yep.
Michael said it would print a byte that represents 5. And people are listing some byte representation like 0101, and Shanghai suggests 53.
Very good. Okay, why is it doing this? Okay, let's go and have a look. And what you'll find is I got this ready in anticipation. This is the Ascii table, right? Printable characters. This is their encoding. There's a decimal encoding here. Decimal here, octal, hexadecimal, binary. And if we go to the number 5, which is what we got here, that's just a number, that's a numeral, 5, notice it's encoded as 53. So what's going on in this code is it's reading the ASCII code for whatever I typed. Okay, it's reading the ASCII code for whatever I typed, and it says, okay, so it's some encoding of the thing I typed. And then what I'm saying is print out a byte value which has this byte value, and it says, oh, a byte value, and it says 53. That you want me to treat that as an integer? 53 is an integer, has the numerals 5 followed by 3. That's how you print out the integer 53. That is not what we wanted, really, I think, okay? And I did that on purpose because I wanted you to think about it a bit. But what we can do is this. Oops, no. If we do this, it says, take the byte I read in and write that byte out in its same format, okay? It's just basically put those bits straight back out again. Whereas here, it's saying, treat this thing as an integer, and turn the integer into a string and print that string out. So it says, oh, that integer was actually equal to the value 53, so that's a 5 followed by a 3. That's the way the string would work. Whereas here it's saying, send a single byte to our standard out and make it come out. So now let's run this and see what happens. Okay, let's run it. And tell me what you think is going to happen now on the chat. Okay, I want to hear what people think is going to happen now when I run this. Okay, let's run it. Takes a moment. Any suggestions there, Leo, on what's going to happen?
Not yet, I guess, because of the delay.
Yep. Now, I don't know if anyone guessed this, but what happened was nothing got printed out. Now, why did nothing get printed out? Did anyone guess that? We got nothing printed out here. So we went from having 53 printed out to having nothing printed out. That green 5 there is what got typed in. That's just IntelliJ recording what I typed. But what got printed out was nothing. Why did nothing get printed out?
Ethan say because it's buffered.
Exactly, because it's buffered.
Just flush it.
Yeah, that's exactly right. Okay, because I forgot to flush it in order to make the point. Okay, so now let's try it again. We run this. Run it again, and we type the 5. And this time we get a 5 printed out, okay? So it's taking that byte and just putting that byte straight back out again. Whereas here it's taking the byte, considering it as an integer, saying, oh, 53, then that's a 5 followed by a 3, and printing that out. Okay, that's why we saw that difference. All right, let's keep moving. What am I going to do next? Oh, now we're going to read from a file. That there was reading from a... reading from the keyboard, system.in. Notice that, system.in. Now I'm going to read from a file. And if you look here, you'll see in the lecture repo, I've put Hamlet, the text of Hamlet. And if you open this up, you'll see it's just, this is the famous Shakespeare play. Okay? So now let's just create a new file here. New file, new Java class, and we'll call it, what are we going to call it? Files input stream. Files input. I'll just call it file input stream. Okay, so now we're going to read from a file. Okay, so first of all, that's a bad idea. Let me rename this. That's why I call it files. There's a reason. Hang on, let's just comment that out. Because file input stream is actually the name of a very important class, which we want to use in this example. So let's rename this, refactor rename. And I'm just going to put a little S in there, call it files. It's slightly awkward, but that will make it that, so now it's changed there, put the S in there, put the S in here. I wondered why I had the S there, that's the reason. Okay, in my notes. Because I didn't want to get it confused with this, okay? So file input stream from Java I/O. That's what we want to use today, okay? So we're going to use that, and we're going to initialize it to null. There it is there. And now what we're going to do is we're going to create a new file input stream, and it's going to be the Hamlet thing. Okay, so it's going to be okay. Now we've got red squiggly stuff. What's that going to be? Let's have a look. Add exception. Okay, we need to, again, we're doing file I/O, so we need to surround it with the try-catch block. Okay, so we do that, and now it's surrounded with the try-catch block. So now we have the opportunity to read stuff in from a file rather than from the keyboard. The last thing was standard in, now we're reading from a file. So let's just read in the first 100 characters. So for int j equals 0, j less than 100, j plus plus. So the first 100 characters in the file, because Hamlet's quite long, I don't want to print it all out. And then we'll say then I'll initialize int I equals in.read like that. So I'm going to read a byte from the input stream. Now look, I've got that squiggly red line again. Let's have a look at what this says. Add exception. Why? Because we could get a different I/O exception. So we had a file not found exception for when I created the input stream. Now I can get a different kind of exception and let's have a look here. I'll add it in there. oops, where did it happen? Oh, I made a mistake. That's not what I wanted to do. I didn't want to do it that way. I wanted to add the block. Add a catch. Sorry, I clicked the wrong button. So now we've got a general IO exception. We could have any old IO exception here. I could have just used the IO exception for both these, but I want to be a bit more explicit just for the sake of the class. And so what we've got here is if this file can't be found, then we'll get this one. If there's an error when it reads, we'll get this exception, okay? And Java requires this, okay? But again, IntelliJ is smart enough that it will help you figure that out. Okay, so now what we can do is we can just say, we can say byte B equals a byte I, casting I into a byte, and then we can just say system.out.write, we'll write the byte, okay? And then what we can do at the end is we can close things and flush, okay? So we can say finally, we'll say in.close, and we can say system.out.flush. Oh, what's happened here? Oh, we can get an IO exception here. That's right. We can get an IO exception with the close. That's all right. Okay, so it's possible that when we try to close it, the file doesn't exist anymore. So it is a bit funny, but with the possibility in our finally block of throwing an exception when we do the close. All right, so now what we've done is we're reading bytes from this file here. This may fail let's just make it fail, like put a typo in there and run this thing. And we'll just see how it fails, just to be a bit clear about it. Oops. Run. And that should fail with a file not found exception, right? Because I intentionally made a typo there. Okay. And then it says here, no such file or directory. Okay. So let's just get rid of that typo and try again. And now it should open and it should be able to read it. And we should see printed out to standard out the first 100 characters of Hamlet. And there they are. Okay, so we can see Hamlet printed out. That's all I wanted to show you there. Now let's do a file copy. Files copy, I think is what I want to call it. Go to my notes again. Yeah, I just wanted to do that. And then what I'm going to do now is I'm going to create...
Steve, sorry to interrupt.
Yep.
Shreya asked a question. I wonder why we don't need to write the exception when we use a scanner class.
That's a good question. Why when we use a scanner class? I guess it's handled within the scanner class. It's a great question. Why don't we need to deal with this in the scanner class? I think for ease of use, the handling of exceptions is dealt with inside of the scanner class. Okay, that's my guess. But very good question. Okay, so what we're going to do now is we're just going to create an output file. Output stream, like that. And I need to fix there's a typo up the top there. It's got to be an output stream too. Okay, and then we're going to let's just call it something like output.txt, and then change this here to write to out. That's our file, like that. And then down here we'll just say out.close, right? Because now we're not using system.out, we're just going to say write.out.close. Actually, we can put it in the same exception handler because it may also throw an IO exception. So like that, okay? So what we've done is instead of reading in and then putting to the standard out, we're now reading in and outputting to this new file called output.txt. Okay, and we're reading in the first 100 characters and we're closing it at the end. Let's see if it works. So this is our file copy. That's only the first 100 characters, which is not really what we want, but it's a good way to start. So let's just run this. It's compiling down here and it's run. And let me see if we've got an output. There we go, output.txt, and there it is. Okay, so we caught the first 100 characters, output this file here called output.txt. All right, let's improve it and make it deal with all of the characters in the file instead of just the first 100. So that's pretty easy. Let's just say this. We'll say while we'll write a slightly fancy while loop here. We'll say int I equals in.read. Okay, so I'm going to actually initialize I and evaluate it. Actually, no, I've got to declare int I up here. I can't do that. Int I up here because it's a while loop. Otherwise, I'd be creating new I every time. So I'm going to do that. Well, let's initialize it to 0 to be very clear. So initialize I to 0. And then what I'm going to do here is I'm saying, okay, let's assign I whatever we read in from the input. And then while whatever we got from there is not equal to -1, which is the symbol for a, what's happened here? Hang on. -1 is a symbol for end of file. What's going on? We've got problems everywhere here. Oh, it's probably just because I haven't finished writing what I'm writing. It's IntelliJ's jumping the gun a little here. We don't want that. We don't want that. Okay, that's better. Oh, I need to. I see. I didn't close that parenthesis. Okay, so now let's see what I've got here. We've created a variable called I. And what we've done here is we've read a byte from the stream, but it's come back as an int, where -1 tells us that that didn't work, and any other value you can cast back into a byte. So now, if we get -1, that means we've got to the end of the file, which is actually what we want. That's what we want to go to the end of the file. And otherwise, we've got a byte and we write it out. And at the end here, we close the two files. Let's see how we go. Run this. Built it, and I guess it's run it. And let's have a look here.
Hi, Steve.
And sure enough, we've got, hang on, Leo. So sure enough, we've got the entirety of Hamlet output instead of the first 100 characters. So we have the, we've done the file copy now, copying the entire file. Yeah, Leo, what was it?
Mike can ask a question.
Mm-hmm.
He has a question about where the buffer is stored. Because you say that it took like a nanosecond to read input from the buffer, but physically, where is the buffer? As you already say, it's not in the RAM or in the...
Oh, okay, that's a little bit of a misunderstanding there. I said it's a nanosecond to read from a register. That's part of the computer hardware. The buffer is actually in memory, which is not a nanosecond. It's if you go back to the slide here, you know, it's a... There you go, it's 10 nanoseconds, very roughly, in that ballpark, okay? So the buffer will be sitting here. A register is, it'll go from the buffer into a register to be used, and it could be used multiple times in the register. Your computer has a limited number of registers, just a handful of them. It's got a large amount of RAM, like, you know, gigabytes of RAM, and then over here it's got disk and so forth, okay? So we're talking about going from disk into RAM, into a register, and being manipulated, then pushed out to RAM, and then pushed out to disk. Hopefully that clarifies that question. We're about to do buffering right now, just to be clear. So far, there's no buffering here. There is no buffering in any of these things, all right? This is not doing buffering. This is doing everything one byte at a time without buffering in this example right here. So what we're going to do next is exactly that. We're going to put buffering in here. So let's do this. Copy this file. We're going to do a shortcut and just do a cut and paste here. Buffering. Like that. Okay. So now we're going to do buffering, and what we're going to do is we're going to write a for loop. We're going to be scientists for a minute. I do performance analysis as part of my research thing, so we're going to do a bit of that right now. I'm going to say, can I use J? Got I in there. Yeah, let's use J for int J equals 0. We're going to do this thing repeatedly so we can get multiple measurements, so we can get a closer view of how long it takes. Okay. So J is less than 20, J++, so we'll do 20 times. We're going to do this thing 20 times over. Okay, so there it is. And then down here, we'll close this. So we're going to loop over this thing 20 times. All right. Now what we're going to do is we're going to start off by initializing this. We'll create a long, which will store nanoseconds in it, like this. Okay, and then before we do the copy, where is it? Down here. We'll initialize that to whatever the current time is. There it is. System.nanotime. Okay, and then what we can do now at the end is we can print out how long that took. We need to do it after we've closed the output file, though. Didn't do that here. After that, we'll close it because the stuff will still be in the buffer until we close, or some buffer or something until we've closed it. So let's just do that. We'll say system.out.print, and then we'll say that took, and then we'll write an expression here. We'll say what end minus start, well, the current time minus the start, right? So system.nanotime minus start, and then let's divide that by let's do it in milliseconds, okay? At least to start off with. So we'll divide by, so that's 1 million times less, right? So it's 4, 5, 6. So it's 10 to the 6. So it's 10 to the 9 to 10 to the 3. So it's six zeros there. Is that 6 zeros? Yeah. Okay. So we're converting from nanoseconds to milliseconds, and like that. Okay. And then what do we want to do? I think that might be it. Let's try running this, hey? So let's run this. So we're not doing any buffering yet, by the way. I'm just getting the measurement stuff working first. So let's run this thing, and we'll get a sense. You'll see there will be actually buffering going on in the operating system, which we don't control in Java. So there will be a change in the results, but let's have a look here. What's going on? Okay, it's a bit slow. So it took 3 seconds. It took 1.7 seconds, 1.7 seconds, 1.8 seconds, 1.6. This particular laptop doesn't have a disk. It's solid state storage. So this is kind of about as good as you can get. So to copy all of Hamlet, it's taking you 1.7 seconds using this. All right, 1.7 seconds. So everyone's seeing that, and we're doing this 20 times over. You can see it's pretty stable. It's just 1.7 or 1.8, 1.66. Okay, but you can see it's about 1.7 seconds to do that. All right, so what we're going to do now is we're going to introduce buffering. First of all, what we'll do here is we will change this. We'll change this to its parent type, like that, and then oh, I need to include them, import them. Yep, import the class. Yep, there we go. All right, so that's just the parent type of that. So it's still, the code still compiles, right? So now I'll say if, and then I'll say false, right? So I'll just turn this part off. So because we want to retain this code. That's the old code that we wrote. Otherwise, do it the new way. And the new way will be to basically do the same thing, but with buffering in place, okay? So for that, we just copy this code over, and we're going to buffer them, right? And to do that, all we need to do is say new buffered input stream, like that. And then the argument is just the input stream that we would have otherwise made. Okay, like that. And otherwise, actually, you know what? I can make this code neater, couldn't I? I could just go like this. Like that. And then I can say if true, I can say in is equal to the buffered input stream or the buffered output stream. Okay, so if I don't have that flag there set, then it's going to just leave them as is. Otherwise, buffer them. Okay, so if true, then we want to buffer them, and we can see what happens here. Okay, now you can give an argument here saying how big you want the buffer to be. So let's start off by making this buffer 2048. There it is. That's the size of the buffer. Okay, that's an argument. It's an optional argument you can give to that Java class for buffered. Now let's run the thing all over again. So remember, we're doing this 20 times, and this time we're creating the input and output, but then we're wrapping them up in a buffered stream. So let's run it now and see what we get. Remember, it was 1.7 seconds, 1,700 milliseconds there. See what happened? Okay, look at that. Look at that difference. Okay, it went from taking 1.7 seconds to taking, 1,700 milliseconds to taking just 50, 30, 25 milliseconds. Absolutely massive difference. We can make this just a tiny bit more fun and interesting by doing this. We could say we can say 1 upshift j, right? What's that going to do? that means shift right, which means multiply, or it means raise it to the power, 2 to the power j. Okay, that's basically a fancy way of writing 2 to the power j. So it'll start off at 2 to the power 0, which is 1, 2 to the power 2, and so forth. So let's see what this does. Okay, it'll give you a clear idea of the effect of the buffer size. Let's run this again. And so now you'll see quite clearly the impact of the buffer size.
Hi, Steve.
Yep.
Should I ask a question? Why does the first copying action takes more time than the following text copying actions?
Could you repeat the question? I didn't follow.
Why does the first time copying take more time than the following text copying?
The following copies, there wasn't much greater when I did it. Well, okay, so I think the question was, okay, in this example here, there's differences because I'm changing the size of the buffer. That's the reason why it's doing it there. But if we go here and change this back to a fixed number and run it again, and I'll try and answer that person's question, like this, run it again. And so I think they were suggesting that it took significantly more at the start. Let's have a look here. So it's taking, there you go, it's taking 50 milliseconds, 20, 38, 50, 56. It's not taking much more in the first time. It is a little bit. And there's a whole lot of reasons why that could happen, including the way the JIT compiler is working in here. There's a whole stack of possible reasons for that. But very often things inside of a system like this can take a while to warm up, and also maybe to do with the operating system's caching. The operating system also has caching. Oh, by the way, folks, don't say caching. I know some people, I don't know why, but some people say caching. It's caching. Just I'll put that out there for you. Let's put it back how it was. So there's one like that, and we'll run this again. And back to how I showed it to you. And again, you will be able to see here the effect of the buffer size. 3 seconds, 3.6 seconds, down to a bit less than a second, down to half a second, and then soon you're in the millisecond range, and eventually you're pretty consistently. In fact, by the time you get to here, let me just be even more explicit here. Just to be really clear so you all know what it is. Like that. Okay, now we can see what size it was, and you can see at some point it plateaued off. It plateaued off around here. I don't know what the value of j was at that point, but once it got to a certain size, it didn't really make much difference if we made j bigger, right? Let's try again. So, yep, there we go, and it's taking slightly longer now. It's funny. It was faster before. There's probably other stuff going on. So that was one of the fastest results. So once we got to about there, after that, it hardly made any difference what size j was. Okay. So as long as we had about a couple of thousand bytes, 1,000 bytes or 2,000 bytes, then the buffering was effective. And with that, we're ready to move on to the next section. Okay. Computational complexity. Now, one of the things I just illustrated to you was a beautiful illustration of a time versus time versus space trade-off. Okay, we made things go faster by using more space. Okay, we made things go faster by using more space. This is a classic trade-off in engineering and computer science, time-space trade-off. And we're going to look at that here in the context of computational complexity. And we're only going to scratch the surface on this. You can do entire courses that deal with a whole lot of things related to this later on in your computer science course. But right now, we're just going to scratch the surface. So what's the context? The key computational resources. We have time, we have space, and we also have energy. Energy is really, really important. We often measure energy. Well, when you say we, in my research, we often measure energy because we really care. Like for the example, the energy efficiency of different memory management strategies, you can make a huge difference. If we can save 20% on the energy consumption of a Google warehouse compute, it's like 20% of that could be the size of a small town's energy. So it's a lot of money and a lot of electricity and a lot of carbon. All right, so time, space, and energy. Computational complexity is a study of how problem size affects resource consumption for a given implementation. Now, I want you to think about, sometimes these things are hard to think about, right? One example I gave to you, I've gave to you multiple times through the semester, which hopefully gave you a sense of it. And that is, we talked about whether you could implement a set using a linked list. And the answer was what? The answer was yes, you can, right? You can use a set using implement a set using a linked list. And if you had a bowl of fruit and your set was limited in size to 8 different fruit varieties, that's a perfectly fine way to implement a set. And when you want to add banana, you've got to search all the elements of the set, but heck, the set's only going to be a maximum 8 size anyway, so you just search that set, and it'll only take you a few steps to find it. But if you're trying to do a census of a large country or some other thing like that, which has millions of data points, that's a crazy way to do it. Why? Because the complexity doesn't scale well. As n goes up, that's a problem size. As n goes up from a set of size 8 for a bowl of fruit to the population of a country with 1 billion people in it, suddenly everything becomes different, okay? And what's important here is we're going to study how the time to finish the problem changes according to that value, all right? According to the problem size. And the definition of problem size can in itself be an interesting problem to solve. If it's the size of a set, well, that's pretty simple. It's the cardinality of the set. So it might be, the population of the country, or it might be the number of different types of fruit. But if it's very often with other problems, it can take a little bit of time to work out what problem size means in that context. Okay, so we can talk about the worst case. What's a worst case thing? Or we can talk about the average case complexity. Okay. Now, computational scaling, what we're doing here is we're talking about identifying an n which characterizes the problem size. And in the example of the one I just gave you, n is the cardinality of the set. So n is 8 in the context of the 8 different types of fruit, and it's 1 billion in the context of the population of a country. So it could be something like the numbers of pixels on a screen, or it could be the number of elements to be sorted. Notice that it could also be, if you think about the pixels on a screen, interestingly enough, it could also be like the x dimension of the screen, which is actually the square root of the number of pixels, right? So it depends entirely on what the algorithm is as to what the right measure for the problem size is, because there's a giant difference between saying n is 1080 versus it's 1 million, right? Where 1 million is the number of pixels and 1 is the dimension on one side of the screen, right? So they're very, very different numbers, and they're very different ways of characterizing the problem, because one goes up as a square of the other, the square root of the other. So the number of elements to be sorted, for example, so we can study the algorithms to determine how resource consumption changes as a function of n. Now, one very simple example would be to say, okay, you could try and have a very naive algorithm where you want to find out if any 2 people in the class have the same birthday. And imagine we're in a real lecture theatre, then what you could do is you get every single person has to talk to every single other person in the room and ask them what their birthday is, and if the 2 people have the same birthday, then you can raise your hand or something. Now imagine that if only 2 people could talk at a time, so the whole class has to wait while each pair talks, right? And if you think about that, that is a lot of little conversations. You can try and do the math in your head in a minute, but think about that. If everyone had to wait because only one pair of people could be asking the question at the same time, think about how many questions get asked in that room. That's an awful lot of questions to be asked, okay? So now let's have a look here. We've got a graph here. Big O notation is something you're going to learn it repeatedly in computer science if you haven't already touched it. But it's a way of expressing the order of the scale of the problem. Okay, big O notation is about the scale of the problem, and we can say if we have a problem of size n that takes some function g of n time to execute in the average case, then you can say that that function g of n. So the black line is you measure this thing. Say you measured it, and that's how long it took. So n keeps going up. That might be like 8 elements. This might be 100,000 or whatever, and this here is how long it takes, say, right? So time up here and number of elements or number of whatever n is down here. Okay, and you measure it and you get some funky function like that. Okay, now the question is, how do we characterize g? And that's what this system allows us to do. It says, first of all, we're going to discard, we're going to allow ourselves to discard values for small n for some value of n, some constant value of n. And you can see there's this weird glitch here, and we're just going to say, oh, let's forget about that part. That's some startup thing. We're interested in how things go on the whole, what the trend is, what the steady state is. That's what we're interested in. We're not interested in this little tiny itty bitty glitch at the start, because if you zoom this graph out and put a billion down here, you won't even notice this tiny little glitch. Okay. Moreover, these two lines look like they're far apart here, but if you zoom this whole graph out and made it keep going, you'd actually see these two things look like they're exactly the same line, because this distance will relatively speaking decrease and decrease and decrease visually as the graph gets bigger and bigger and bigger. And what we see here is a constant factor in front. That's C. That's the difference between these two things here. And what we're saying is that G is described this way. It's in the order of function f if and only if there exists some constant C, that's a constant offset, and a constant n, such that for all n which are bigger than that constant, then g of n is simply some constant multiplied, is less than or equal to some constant multiplied by that function. Okay? So if you can fit it under there, under that function. All right? Now, that might sound like mathematical garble to you, but basically what we're trying to do is try to get a function which approximates this in a rigorous kind of a way. Okay, so we're going to ignore little glitches at the start, and we're going to ignore constant offsets. Okay, so, oh, there we go. So there, for example, f of n, okay, that's f of n, that's where it's linear, f of n, and you multiply that by a constant factor, 3, and we're going to say that they're the same. So f of n is, both 3n and n are in f of n, are O(n), okay? They're in order n, because the difference between these two is a constant factor. Okay, the difference between those two lines is a constant factor 3. Okay, so we're treating them as the same, because all that's changing there is the slope, and they've got the same overall characteristic. Okay, so some simple examples. Now, what I want you to do is put in the chat any examples you can think of that fall into these different categories of complexity, computational complexity. Things that are always happening in a constant amount of time. The amount of time they take is a constant number. Okay, what things or operations in things we've done in class so far would fit into constant time, logarithmic time, linear time, n log n, or quadratic time? Can anyone think of any examples that fit into any of these? Leo, can you let me know if you hear any examples?
Not yet. For just a second.
I'll give you an example of a constant time. A constant time might just be an arithmetic operation, or it might be something like a hash function. A hash function should be constant time normally, okay? So a hash function would normally be constant time. So the hash function might be a multiplication, or it might be, the example we gave early on in class was something like integer remainder. That's still a constant time thing. It's integer remainder, it's a single operation, okay? It's an expensive operation maybe, but it's still a single operation, it's constant time.
Now we have several, so linear can be searching through a list. And,
yep.
Logarithmic could be searching through a binary search tree or merge sort. And constant can be print out hello world, or whoops.
Okay, I've got a question for you. So one of them was that linear can be finding something in a list. This one here can be finding something in a binary search tree. Then I think someone said that merge sort was also log n. I want you all to think about that. What is merge sort log n? Okay, does anyone have any answer to that? Is merge sort log n?
Joshua just said it's n log n.
Very good. Okay, so logarithmic. Notice that I wrote in here a balanced binary search tree, because if, as you all know, you're all familiar that finding an element in a unbalanced binary search tree could end up being linear, because an unbalanced binary search tree in the end looks like a linked list. Time to find an element within a list, n log n is average time to sort using merge sort. And quadratic, the example I gave you, the birthday, that's an example of a quadratic thing. Every student has to talk to every other student, okay? Now, counting statements. One way you can try and work this out is by counting statements. There are traps here because some simple statements are constant time, but other things may have arbitrary complexity depending on what they are. So there's a little bit of trap here, but this gives you a bit of a guide perhaps to how one might look at the time complexity. So if we look at this here, consider hashing into a table of n elements, then your hash function is this. So it's integer remainder, and that there is constant time, okay? Then here is summing a list of size n. You can see here there's an operation here. What's that? The complexity of that operation there? Well, that is constant time, but then it happens n times. Okay, so you count this, and it happens n times over according to the length of the list. Okay, so depending on the length of the list, this constant thing here will happen that many times. So it's order n. Okay, now let's look at something more complicated. What we're going to do here is just go and count things out. And we can see that first thing is clearly constant time. This thing here happens n times, n in the number of values. So you've got some array of values. Okay, it's a list of values. And that loop there is going to go around according to the number of values in that list. Okay, then the next one is going to do this, is almost going to do the same, but notice that it starts at I plus 1. That's interesting. Okay, so it's going to go around I plus 1 times. So what is the complexity of this line? Okay, well, it's interesting. If you do this a little bit of maths here and say, okay, n minus 1 plus n minus 2 plus that equals this, okay, which ends up being n minus 1 multiplied by n, multiply n because of this outer loop here, divided by 2, okay, which basically ends up being linear time. But we'll leave that there like that. And then everything inside the loop is going to have the same complexity, okay? But to work out that there, you need to know this thing here. You can work out an approximation to it in your head fairly easily, I think. And then what you do is you find out that the complexity of the whole thing is equal, the number of, if you count these all up, you end up with 1 plus n, because that thing there is taking n, plus 4 times this, okay? Which is equal to this whole expression here, which equals to 2n squared minus n plus 1, which is in the order of n squared, because this dominates and that's the constant factor. Okay? Hopefully that makes sense to folks. Now let's go, before we go to the mini quiz, in fact, while you do the mini quiz, I'm going to now do some code on computational complexity for a few minutes. And hopefully I can still finish this lecture on time. So there's the computational complexity mini quiz. Now we're going to do some code. And what I did is before the class, I went and created another very simple little example here. And I got our BST binary search tree set and our hash set from here, from A05, and put them in here and wrote a very, very ugly, simple little thing called complexity, which allows us to look at the complexity of doing some operation lots of times. Now let me go here. I'm going to get rid of this first, comment that out. I'll uncomment them in a minute, folks, so don't worry. If you're not missing out on anything, I'll comment all that out. All right, so what I'm going to do is I'm going to draw a graph, and what it's going to do is it's going to create a binary search tree set, and it's using a whole bunch of words. Where are the words coming from? They're coming from the dictionary. Where is that code? It's going to read them in from the dictionary, which is here somewhere. Oh, there it is. It's going to read them in from the dictionary. Okay, so it's going to read in all those words from the dictionary, and that's just the standard dictionary. Okay, there it is. That's your dictionary. All right. So now let's have a look at what happens when we do Okay, we've got two different tests we can do. First of all, putting things into the set. And then we can search for things in the set to see if it contains. Okay, so I've got two tests. One is to populate and one is to contain. So I'm going to start off just by drawing two graphs, both the same color because they're doing the exact same thing. I'm just repeating it. Maybe repeat it 3 times over. So we can see 3 experiments, results from 3 experiments, all on one graph there. And all they're going to do is they're going to put all the words into a binary search tree. Okay, and we do it, repeat the experiment 3 times over. Okay. So we're just going to do 3 experiments exactly the same, and we're going to run this now and plot them on a graph using JavaFX. Okay, very, very simple, not very pretty graph. And let's see what happens here. It's building. Now it's shifting to this screen here. Oops, I just noticed my laptop is not plugged in, which is bad. And it's even on low battery. Let's plug it in. We're waiting for this thing to pop up. There it is. Okay, now can you see that? Hopefully it's big enough that you can all see that. It's not scaling. All right, so it's a bad window. But all right, let's have a look here. Hopefully that's big enough that you can see it. Let me see if I can do this. No, it's not going to even zoom if I do that. Perhaps if I do that. Nope, that was a bad idea. All right, we'll just leave it as it is. Oops, maybe. All right, that didn't work. There's your graph here. Okay, there it is. Okay, what shape is that curve? Does anyone know the name of that shape of that curve is? Can you see the shape of the curve? So there's a data point here, data point here, data point here, data point here, data point here. And it's roughly, the curve is roughly like this. What do we call that? Does anyone on the chat know what the shape of this curve is? Okay, got a very noticeable shape. Anyone know what the shape of that curve is?
Stanley said it's parabolic, and Michael said it's polynomial.
Yeah.
Said it's exponential.
Yeah, it's something like that. It's going to be one of those. Okay, it's going to be something. It's definitely not linear, right? Okay, but why? Why is it going to be? Why is it going to be like that? Look at this, folks. Look at this. All I'm doing is adding words into our binary search tree. Why would it do this? What should be the complexity of adding something? What do I need to do to add something into a binary search tree? Okay, I need to first find out if it's in there. Once I found out if it's in there or not, then I get to add it, right? So that should be, to find it if it's in there, it should be n log n, right? No, it should just be log n, right, to find out if it's in there. But it's taking some times n because I'm going to add n elements in there. Okay, so it's going to be n log n, right? So that's what you expect, but that's not n log n. It's something much scarier than that. Why? It's probably an n squared curve there. Why would it be n squared? Can anyone guess? Here's your big clue, folks. That's your clue. What's that telling you? Something strange is going on there. All right. No one got it? Has anyone guessed it? Maybe, I know there's a lag here, folks. Let's try this. Yep.
No, not yet. Michael just said the size of the set is increasing.
Yeah. What's going on, folks? Think about it. Is that dictionary I just showed you? What order is it in? It's sorted. That's just how the file came, right? So what I'm going to do now is I'm going to shuffle those words and try again. What do you think will happen now? Any suggestions there? What's going to happen when I sort that list of words? Okay, so this is the sorted one, and this is the unsorted one. Why is that? That's the unsorted one, it's the randomized one. Here's the randomized words, and that is the sorted, that's the words in alphabetical order. Alphabetical order is the light blue, randomized words is the dark blue. Why?
You can suggest the sorted one would make it n squared.
Exactly. The sorted one would end up being n squared. Why? Because our binary search tree would end up looking like a linked list. And if it's a linked list, then it's going to be n squared. Because every time I try and put something in there, it'll be equal to the length of the list, which is in the order of the number of elements I'm putting in there. So it's basically n squared. Whereas this one here should be n log n. So this is approximately n log n, and this is approximately n squared. So this is really interesting. It's telling you two things. One is how to characterize the complexity of something, and also should give you a really good insight into the behavior of binary search trees when you put data in there which is in a particular order. Yeah, any questions there, Leah?
I think Shazan just pointed out exactly what you just said.
Fantastic.
Yeah.
Okay, now let's... Okay, what I'm doing now... What I'm doing now is I'm putting... Oops, I accidentally did the wrong thing here. What I'm doing now is I'm adding a binary search tree, which is coming in, I think, in orange. So not a binary search tree, a hash set. So we looked at a binary search tree set. That's what we just spent a few minutes looking at. Now we're looking at a hash set, and we're going to put things into the hash set. All right? You might want to remember how we built that hash set, if you can think back. Look, the hash set is in gold. The binary search tree is in blue. What the heck's happening? Does anyone know what's happening here? The gold one, which is this shape, it's even worse than the blue one. Why would that be? The gold one is at least as bad. Let's just assume it's an error at the moment. Why is the hash set behaving so badly? We're inserting things into the hash set and we're getting very, very bad behavior from it. Why would that be? Let's look at the code. Can anyone see anything right at the top of this file? We've only got two elements, two buckets in our hash set. We put that there for testing. Okay? That means we've just got two linked lists. Everything is going into two linked lists, and we're pulling like 40,000 words into them. So we've just got two linked lists. It's going to behave very much the same as a linked list. Okay? So we've got the same problem again. The fact that it was different to the binary search tree, I consider that to be an experimental error maybe, but the real point is that we've got this very bad behavior because we only had two buckets. So what I've done now is I added a new method here which allows us to create a hash set of a particular size. So instead of making default buckets, which is 2, we can specify how many buckets it's going to be. Let's see what happens when we do that. Okay, so now the orange and the red are going to make it have 20 buckets and 1,000 buckets respectively. Let's see what we get. Stop this, start again. Bit more work for this thing to do now, so it's taking a little longer. Okay, there it is. Now we're now looking for the orange and the red. So the yellow was the hash set, inserting into the hash set with just 2 buckets. The gold is with 20 buckets, and the red is with 1,000 buckets. So you can see the red is now looking pretty good, and there's an enormous difference. That's showing you how much impact it has when you change the number of buckets in your hash set. Okay, now having done that, let's move on and do look at contains rather than populate. I'll just comment this out. We'll do the same sort of thing here. Let's start off with I guess we can just put them all on the screen at once to finish this part of the lecture up. So what we've got here is now we're going to, we've got the words in the set. Okay, so we've created the set, and contains test is going to take those words and then do tests to see if it contains it. So it has to put them in first. It goes, puts them in. Once it's done that, it then checks to see whether it contains the particular words. All right, so now let's have a look at how long these take. And again, we've got the same thing happening with a hash set. I've started off with 1 bucket, 20 buckets, and 1,000 buckets for contains now. So previously we were looking at populate, which is putting things into the set, and now we're looking at contains. So they've already been put in, and now we're just looking at how long it takes to find things in that set. And you can see here, now the shape is more linear, but you can see which is what you'd expect, okay? To find out if something is in a linked list is linear. To do an insertion of n elements into the linked list is going to be n log n, so it's going to be n squared, right? But if to actually do the simple check to see if something is in there, you're going to get linear, which is what we see here. You see a linear thing here, you see a linear thing here. And if we have a large hash set, look, it's almost constant time down here. See that? That's the red one there. So it's a hash set. It's a big hash set with 1,000 elements. That's with 20 elements. And this one up here is with 1 element. Okay? And what you can see here is the effect of making a large number of buckets. Sorry, when I said elements, I meant buckets. So that's with 1,000 buckets. That's with 20 buckets, and that's with 1 bucket. And this one here, these two here are the different You can see it's a little bit noisier because they're quite far apart when I've run it twice. But that's the tree. But this one, the yellow one, the gold one, and the red one, they are the hash set with 1,021 buckets, and you can see that the number of buckets makes a very big difference to the slope of that curve. Okay, and it's approaching a constant time once you make it sufficiently big. All right, with that, we can move on to the next part of the lecture. So the last thing we're going to do is talk about formal grammars. So I don't know how much you all like grammar at school. I never really liked it very much. I want you to think for a minute about language. Many of the people in this class know more than one language, which is really impressive. And I want you to think about what you know about language, and also to think about the relationship between what we call a formal language and what we call natural language. Does anyone know what a formal language is? Can anyone give an example of a formal language? I'll give you a hint. A natural language is like Chinese, English, Hindi. They're all natural languages. We call them natural languages, okay? German, Spanish, natural languages, okay? So if that's a natural language, what is a formal language? Anyone know what a formal language is? A formal language is synthesized, okay? It's a synthetic one. It's a mathematical concept. And an example of a synthetic language is something like Java. Java is a formal language, but you can have all kinds of formal languages, but programming languages are one example, okay? So we've got a grammar in our programming language, you've got a syntax in our programming language, but it's rigorously defined, and there's some standard that defines it, whereas a natural language evolves and is transmitted from person to person over time, and anthropologists and linguists study this stuff, right? Natural languages are rich and complex in ways that formal languages are not. Okay, so formal grammars. Formal languages are distinguished from natural languages by their artificial construction. Someone made this thing from scratch rather than natural emergence. So natural languages, whichever language we speak, is made, it emerged naturally. So English, for example, has a background in a whole lot of languages, including Germanic languages. Okay, it didn't just one day appear out of the blue. Noam Chomsky, the guy on the right there, is often credited with opening the field of formal grammars while studying natural languages. Okay, so he's an interesting guy. So some of you may know him for his politics. He's famous for that, but he's also very famous for his work on language, and in particular this bridging of formal and natural languages. And he's got all sorts of theories about how language is formed and so forth. Very interesting guy, and interesting. In computer science, we talk about Chomsky grammars in computer science, and that's named after him. He, I believe, is still a professor at MIT. So, a generative grammar here, we can talk in English about a sentence being constructed out of a noun phrase, a verb phrase, and possibly another noun phrase. And so a noun, we've got a little thing here which I'm going to explain in more detail in a moment, which says that nouns are going to be made, we're going to have 3 different nouns there: signs, directions, and lives. And the article is going to be the, and we've got verbs which are show, matter, look, and adjectives which are big, small, white, and black. And a noun phrase is going to be an article, possibly followed by an adjective, possibly followed by a noun or a noun phrase. Okay, and then a verb is a verb or a noun phrase, or possibly followed by a noun phrase. All right, so you've got a sentence with a noun phrase and an article and a noun, like that. And so what we've got here is a sentence that's actually a good English sentence, a proper English sentence. It's, the signs show the directions. Okay, so the signs, so in this case, sign is a noun, the is an article, and show is a verb, and then you've got another article there, which is the, and then you've got a noun called directions. All right, and then, but the thing is, that grammar there also allows you to construct sentences that make no sense in English. So you could say small, big, directions, matter, the black, white signs. That's nonsense, okay? But it is allowed by the grammar that's provided, okay? So it's legally, it's a legal sentence in terms of that grammar, but it's a nonsense sentence, okay? So this is a very important point, because the grammar is not about meaning. Meaning is semantics. The semantics of that second sentence are nonsense. The semantics of the first sentence are clear in English. Grammars don't tell you about semantics. They don't tell you anything about whether it's meaningful. They just tell you whether it follows this rule. Okay, and you can see the rules there, and you can see two sentences there which both follow the rules, one of which is meaningful and one of which has no meaning at all. Okay, that's an important point because sometimes people think that the grammars are going to tell us the meaning. They don't tell us they have anything to do with the meaning. They have to do with the construction of what's presented. So we often talk, when we do this, we often use a thing called EBNF, Extended Backus Now Form. And there you can see Nicholas Wirth. He's a Turing Award winner, and he was one of the people responsible for EBNF. It's a standard way of representing the syntax of a formal language. And again, I've put stress here, but not the semantics, okay? It doesn't tell you anything about the meaning, it just tells you about the arrangement of the words, okay? Or the arrangement of the symbols, okay? And it's got this notion of terminal symbols and production rules. Okay, so EBNF looks like this, the very basic syntax of EBNF production rules. You've got an equal sign, what we call an equal sign, it defines a production rule. This will make more sense when we start doing examples, which we're going to do in a few moments. A vertical bar, which sometimes we call a pipe. You can see that on your keyboard, perhaps above the backslash key. The vertical bar identifies alternatives, so you can see three things there. You've got three alternatives. You've got the character 1, the character 2, the character 3. Notice these are what we call tokens sometimes. These are characters. It means there's no concept of an integer or a value. There's no concept that 1 is less than 2 or anything like that. That's semantics, and this has nothing to do with semantics. It just says there's a symbol here, which is the symbol 1. There's a symbol here, which is a symbol 2, and there's a symbol here, which is the numeral 3. Okay? And so then that thing there says that we can have any one of those three things. And the curly braces have a very particular meaning. They identify expressions that may occur 0 or more times. And so, for example, if you say 1, comma, curly brace, 0, curly brace, what that means is that this pattern here allows one that it only allows patterns that start with the symbol 1, but after that it can have 0 or more 0 symbols. Okay, so for example, the 100, which we'd interpret as 100, 100 would be a legal thing there because it's got a 1 followed by 2 zeros. Likewise, the number 1 would be legal as well because it's a 1 followed by no zeros. And likewise, the number 10 would be legal because it's 1 followed by 1 0. But the number 11 would not be legal because it's a 1 followed by a 1, not followed by a 0. Okay, and then the square braces, and you can see the square braces on your keyboard is below the curly braces, and they identify expressions that may occur 0 or 1 time. Okay, so just 0 or 1, like a Boolean if you like. And so, for example, if we say 1 followed by the square brace 0, means that it's either going to be a 1 on its own, or it's going to be a 1 followed by 0. That will not admit will not allow the pattern 1 0 0. That's not allowable there because this one here only allows a single 0 or no 0. That's what the square brackets mean. And then a comma means concatenation, so it means followed by. If you speak it out loud, you might say 1 followed by such and such. That's what the comma means. And then the dash means an exception. You can say it's like this except not that, right? So you can define exceptions. Sometimes that's really useful because sometimes saying all the stuff can be rather hard, rather time consuming. Just say it all out. Say it's like this except there's 1 or 2 exceptions. That's what the dash sign allows us to do. It's like a minus sign. And then you can group things together with the parentheses like this. And then here we have a way of saying that's the end of the rule, a bit like the semicolon at the end of a line in Java. All right, now you think, wow, that's a bit of a mouthful. This is not so bad. If you've done a few examples, this will make sense. And if I give you one of these in the exam, which is very likely to give you one of these exams, almost every exam I've given one of these, I will provide to you this. You're not supposed to remember any of that stuff I just put on the slide. You're supposed to understand it, but you don't need to remember that there. So I would provide you that with the information that's on the slide there. You'll see that example in the 2021 semester 2 exam. You'll see an example of a question on this, and you'll see that I provide this notation, so you don't need to memorize the notation. All right, so if you just go to Wikipedia, you could find, I don't know if it's still there, but I scraped this off Wikipedia at some point in time. And it's for some very strange little programming language, which is defined this way. And you can see these production rules, 2, 4, 6, 8, 9 production rules, okay? And now notice that down the bottom there, they've got this strange notation there with the question marks, and basically they're saying, rather than typing them all out in their notation, they're just sort of saying, oh look, when I say all characters, I mean all of the characters that are visible, so like all the stuff on the keyboard, right? And the question mark means, you know, use common sense for this, right? And white space, likewise, they're just saying, oh, it's just all the white space ones like the tab and the space bar and stuff. Okay, so they're not actually spelling it all out. Whereas the digit, they've spelt it all out. And for the alphabetical characters, they've spelt them all out. And then they've got an assignment thing, which is what they call an assignment in the language. Like, you know, in C, when you say I equals 0, that's an assignment. And the assignment would be an identifier, like, for example, the letter I. Then this special symbol here, which some of you may know was used in some old programming languages like Pascal. And then a number or an identifier or a string. Okay, so what the heck's a string or a number or an identifier? Well, they're just defined up above. So sometimes it's easy to read these things from the bottom upwards, right? Because it's pretty obvious what a digit is. It's pretty easy to understand what an alphabetical character is. Now it's easy enough to understand an assignment, which is that's the key thing in the assignment. It's going to have an identifier with that, and then on the right-hand side, it's going to have a number or an identifier or a string. And you know what a string is here? It's a string is going to have a double quote, followed by all characters except double quote. So the minus means except. So it's all characters except double quote, and all characters is all visible characters. So all characters except double quote, followed by a double quote. Okay? And then here a number allows an optional, so 0 or 1 minus signs at the front, followed by a digit, followed by multiple digits. Okay? Followed by 0 or more digits. Okay, that's what that notation says. That means 0 or 1 minus signs, followed by a digit. Digits are defined down here. Followed by a 0 or more digits. And then an identifier is an alphabetic character. So it's going to be one of these things. Followed by an alphabetical character or a digit. So it means you can have digits in your identifiers, but the first character of the identifier must always be an alphabetical character. Okay, and it can be just one character long, or it can have multiple of these built behind it. Notice the use of the braces here to make a group, saying that it's going to be this, followed by this, followed by this. That's what the parentheses are meaning there. And here we're saying our whole entire program consists of the word program, followed by some white space, followed by an identifier, followed by white space, followed by the word begin, followed by white space, and then 0 or more assignments, followed by end with a full stop. That's the whole program, okay? So the program is going to have this, followed by identifier, which is perhaps the name of the program. I guess that's what that means. Remember, this doesn't encode semantics, so we have no idea what it means. But it's going to identify there, and then it's got a begin and an end. Okay, so hopefully you understood that basically. Can anyone in the chat tell me what's strange about this language? It's a bit silly. This is a toy. This is a toy thing. There's some very obvious kind of limitations / problems with this. Can anyone notice anything that's kind of a bit silly or a bit naive about this? And just put it in the chat, and maybe Leo can call them out. Now we're going to look at an example in that program. There it is there. Program demo 1, begin, and then it's got a bunch of things there. Okay. So for example, that's the identifier of the program. It's called demo 1. It's got an identifier there. It's got an assignment followed by the and so if you look here at the assignment, it's going to have a number. Okay.
Steve,
yeah, hang on, just yep. Go ahead.
Why do we? Julian asked, why do we need white space here?
Why do you need white space where?
So in this grammar.
Well, imagine. Okay, you know what white space is. So the question was, why do we need white space in this grammar? Okay, and the answer is, white spaces are spaces and tabs. Okay. And now, why do we have spaces and tabs in this program here? And new lines, all those things are white space. Well, it's to help us understand, a human read it better. Imagine if you didn't allow any white spaces. If there were no white spaces, then how would you separate this word program from the word demo? You'd need some way to separate them. You could do it using something else, like the number 0, but that would be really weird then, because you couldn't use 0 for any other thing, and it'd be really hard to read. So part of the answer to why we have white space here is because as humans, it's a lot easier to read if there's white space there. Likewise, there's an indentation here, which makes things easy. This doesn't tell us that we need much indentation or any indentation. If you look here, it says nothing about indentation. It just says there's allowed to be white space. But the indentation makes it a lot easier to read. Okay, so that's why white space is useful in a programming language, and because it separates things. You got this one is separated from that one by some white space. That's one reason, and the other one is aesthetically. It's an awful lot easier to read than if you just didn't have any separations. We need that separation so we can actually make some sense. The computer can make some sense of it, but also it makes it easier for the human. All right. Any other suggestions about what's limiting or silly about this little tiny toy language? There are at least two very silly things about it.
Yeah, Yan suggested so alphabetic should include lowercase as well.
Okay, the person's always shouting, right? It's all in uppercase. Yeah, fair enough. Yep, the symbols here are all in uppercase. There are languages like Fortran for which this is kind of true. Yeah, but there's something actually kind of really more, that's just a little bit annoying. It means it's kind of always a bit in your face. It doesn't actually limit what you can do. Is there any other things that are actually kind of weird here?
Yep, Michael said you can only ever assign values.
Yeah.
Things.
That's right. You can only assign, this whole language only has assignments in it. So it means you can just say this equals this, this equals this. You can't do anything with it. So it's a very limited language. What else we got here? Anything else?
Students are also suggesting that we can't have any conditional statements, no loops.
Right.
Because there's no boolean.
So there's nothing other than assignments in here. There's one other thing that's a bit funny. If you look closely, the numbers, they're allowed to have a minus sign even if it's even allowed to have a 0 at the beginning of the number, which is weird, right? If you actually wrote a number, you wouldn't normally put a 0 at the beginning of your number. That's just convention. When we write numbers, we don't write 0, 3 normally. We normally get rid of all leading zeros just as a matter of convention. But this thing here doesn't stop us from putting all sorts of zeros at the front, which is pretty weird. I guess it's legal, it's just a bit strange. Okay, that's great. I think you understood that. Now let's go through some examples. This could be hard. So what is a grammar? I want you to try and write this in the chat if you can. I'm going to give the answers on the slide. This is something in the class. It's a lot more fun when we've got a real in-person class. And I feel so sorry for you guys having this lockdown semester. Well, it also sucks for me too. It's a lot more fun when we're in the room together. What I would do here is try and solve these things together. How do we write a grammar for the natural numbers? Okay, grammar for the natural numbers. Okay, I'd like you to try and think of answers to all these. So try and type them into the chat. If you can think of any things here, these start getting a bit tricky. Decimal numbers is a bit tricky. 24-hour time on a digital clock is a bit tricky too. Okay, but I'm going to start off with this. Remember, semantics don't mean anything here. It's not about semantics. It's about what's legal to write. Okay, now I'm going to start off with the natural numbers to get the ball rolling. So let's again work from the bottom up. And we'll say digit is equal to all of the non-zero digits, NZ digit, not New Zealand digits, non-zero digits plus 0. So I've gone and defined the NZ digits here plus the digits. I could have done it the other way around. I could have defined the digits to be everything and the NZ digit to be digits minus 0. That would be a perfectly good way to do it as well. Okay. But I've got, so here what I've done is I've got a thing called NZ digits, which are non-zero digits, and I've separately got the digits which include 0. All right. Now, here I've got the natural numbers, which is equal to 0, which is a natural number, or any non-zero digit followed by some number of digits. Okay. Natural numbers are non-negative. Okay. So we don't have to worry about minus signs. And you can see here that we've got non-zero digits because we don't have a leading 0, because that's not the way we normally write natural numbers. We don't normally have leading zeros in natural numbers. So here I've said it's got to start with a non-zero digit, then it's going to have it's going to have 0 or more digits following that. So you can have trailing zeros. All right, so how would I do integers? So integers are much like natural numbers, except that you can have a minus sign. And there's something else a little bit subtle and interesting about an integer. Has anyone got any ideas there? What's interesting about an integer is that we want to make sure that this minus sign doesn't go in front of the 0, because we don't normally write minus 0. That's not meaningful. That's not how we normally write 0. So we only want to apply this minus sign to the non-zero numbers. Okay, so we've described here, I've assumed that we've got non-zero digit and digit already available to us. I didn't write them out in full. I mean, you'd write them out in full if you were giving a full answer here, but to save space on this PowerPoint slide, I've just written integer in terms of non-zero digit and digit, which are defined right there, okay? So now we've got 0 or a non-zero digit followed by some number, 0 or more digits, with an optional minus sign in front. Okay, hopefully that makes sense. Have we got any answers on the chat, Leo?
Yes, but it's really hard to read it out.
Oh, no worries. No worries. I can just charge ahead here, and it is hard to make it interactive for this particular one here. So this is interesting and a little bit complicated, folks. And so if you've got ones in the chat, if people have put ones in the chat, you might want to see if there are errors in it, because it's actually quite hard to get this right. So what I've said here is I've defined a whole lot of possibilities, and I've excluded, so at the end here I've said, but don't include -0. So I said excepting for -0. So this whole thing here doesn't do a special case for 0. So it includes the possibility of 0. And right at the end here I say, oh, but don't include -0, right? So that's how I've written it. So what I've said is there's an optional minus sign in front, followed by a natural number, which we just defined up here, okay? Followed by a full stop, an optional full stop, so there's 0 or more of these. So a decimal number can just be a natural number, right? That's okay. And it can also be a, it can also be a, it can also be, well, if you just looked at this, you could get -0, but remember we've got the special thing here excluding -0 at the end, okay? But then what you can have a natural number followed by a non-zero, followed by a digit, and we always have a non-zero digit at the end, okay? The reason why we have the non-zero digit at the end is because we don't have trailing zeros at the end of our decimal numbers, right? So that's what the significance of that. If you did this in a very simple way, you could have a trailing 0. And if you did this the wrong way, you could have a leading 0, both of which are not sensible for decimal numbers or natural numbers or integers. Okay, now let's look at 24-hour time and a digital clock. So we can think of time as being made of an hour followed by a colon followed by a minute, where an hour is going to be either a 1 or a 0 followed by a digit, and digits defined up here, or it's going to be a 2 followed by 0, 1, 2, 3. Okay, so if the hour, if the leading digit of the hour is 0, then we're allowed to have 0, 0, 0, 1, 0, 2 up to 0, 9. If the leading digit is a 1, we can go 1, 0, that's 10, all the way up to 1, 9, which is 19. Okay, but otherwise we have to have the 20s, and we've done this very carefully, so we only have 20, 21, 22, and 23, which means that we don't have numbers like 99 or 76 or whatever in our hours. So that this description here allows us exactly 0, 0 up to 23. They're the 24 possibilities for the hour. Okay, and then for the minutes, we've got similar sort of thing here. We've got 0, 1, 2, 3, 4, 5, followed by any digit. Okay, so you've got that gives you all 60 digits, starting off with 0, 0, ending up with 5, 9. So 0, 0 to 59, and this allows you to have 0, 0 through to 23, is 2, 2, 3. Any questions about that? Any questions?
No.
Fantastic. All right, we're ready to go with the next mini quiz. And we're getting so close to finishing the semester. We're on track. There we go. I've just launched the next mini quiz. And we're going to finish up with one of my very favorite bios, Robin Milner. Now,
Oops, sorry, Steve.
Oh, you did get a question.
Pops up a question. Could we recursively define the EBNF grammar in itself?
Recursively define the grammar in itself. I don't even know what that question means. Maybe they could give an example. Recursively define the grammar. So this is a definition of a grammar. You could, well, that sounds like a very strange thing to do. You mean to write a grammar for the grammar? that's the grammar there. So write a grammar for that grammar. Maybe I don't think, maybe I don't understand the question, but that sounds like a very strange thing to do. Certainly we're using recursion here. We are using recursion a lot here, in case you're wondering. So you're defining NZ digit here, for example, and then actually we're not using recursion in it. Are we using recursion here? No, none of these ones are recursive. For it to be recursive, you'd have to have the same thing on the left and the right. And none of these ones are. It's not uncommon to have a grammar which is defined recursively. That's quite common. But I'm just looking here and reminding myself, actually none of these ones happen to be recursive. So recursive grammar is quite fine, where you define something like an NZ digit in terms of an NZ digit, or at least a mutually recursive one. That's quite possible. But I still don't really understand the question.
I think Ethan didn't further specify, so
okay.
we can.
All right, let's move on to our bio today. We've got a great bio. So today's bio is Robin Milner, one of my favorite bios this class. I have lots of favorites, but he really is one of my very favorite ones. And he won the Turing Award 30 years ago, believe it or not, and when he was in his 50s. And he, if you come and visit my office after the pandemic, you'll see there's a room right next to my office. I was involved in redecorating our building, and I put the big portraits of people who I like the most there, and Robin Milner gets a room. So the Robin Milner room is right near my office, and it's got this beautiful photograph of him there. And he was a very nice, generous man, a very decent man, as well as being one of the most brilliant computer scientists. And the Turing Award citation for him is one of the longest in all of the history of the Turing Award, because he got the award for doing so many different things. And there are three of the things are listed on the slide here. One is automated theorem proving. This is an incredibly important idea. So this is where you have human assistant, you have a machine assisting a mechanical prover. And what that's all about is saying, let's try and prove something formally and have a machine help us do it. And this is about formal correctness of programs in particular, but people also use them in mathematics. But you may have a human assisting or not assisting. The person in the office next to me in computer science, Michael Norrish, who is an academic in our department now, he is the maintainer of one of the important theorem provers. It's called Hol 4 is Michael's theorem prover, and that came from Robin Milner. From that was where the legacy came from Robin Milner. And this is about the really interesting science of rigorously proving the correctness of programs or mathematical theorems. And Robin Milner developed a language called ML, which you should all know of. If you haven't, then that's fine, but it's one you should eventually know of. And it's something which we could teach here. Some of you have heard of OCaml, maybe. OCaml is based on ML. Some of you have heard of Standard ML of New Jersey, SML, and that's another ML. And the other ML language, which some of you may have heard of, is F#, which is actually developed by an ANU graduate who was influenced by Robin Milner. ML is very important, among other things, for having the first parametric polymorphism, which is the father of today's generics. And it's absolutely no accident that Don Simon, the guy who invented F#, was also responsible for getting generics correctly implemented in .NET in Microsoft. And him being a student of ML knew a lot about how to do that well and did a fantastic job of it. Pi calculus, which is a formalism for describing the properties of concurrent computation. So what I like about what Robin's done, I mean, he did a lot of great stuff, but was putting rigor into computer science and allow us to reason about the correctness of the things we're doing, including concurrent things, which is a really very interesting and challenging area. He was also a delightfully modest man. I knew him when I was a PhD student because he used to visit ANU, because he was very good friends with one of the professors at ANU. And when he used to visit, it was Malcolm Newey, who was a very good friend of, who's one of the senior academics there. Malcolm's retired now, but when Robin used to visit, I had no clue he'd won a Turing Award. I didn't have the faintest idea he won a Turing Award, and I used to have morning tea with him and so forth. It wasn't until years later I discovered that background. Anyway, fantastic man, very interesting guy, and had a really big impact on computer science, including programming languages, which is one of my main areas. Now, we're pretty much right on time, and the next lecture will be on Friday, where we're going to do concurrency and threads, which is always a fun lecture. And that is our very last lecture for the semester of the main content. The following Monday, that is a week from today, we're going to do a revision lecture where we revise for the exam. And remember, you need to submit questions to a Piazza. I'll put a post on Piazza and I'll invite you to submit questions for your what you want me to cover in the revision lecture. If you don't submit any questions, then I'll just make up whatever I want to cover, and you won't have an opportunity to engage. But I'm giving you the opportunity. You just need to make the most of it. All right. Have a great week, and don't forget the assignment deadlines. I'm sure you won't. And